Now here we have a picture of the situation we've been looking at, okay? I got room in there? Okay, well, let me put these down. Okay, the hemisphere is again badly represented by this picture, but we understand what this stack is. Okay, it's the IJ stack with Z partitioned into P sub IJ subintervals. Okay, so you have the XI strip. Within that strip, you have a delta Y, delta YJ. They're giving you this little rectangle, and above that rectangle, you have this stack. So within the XI strip, of course, you have one of these stacks for every subinterval, and it ends up looking something like this. Pretty badly drawn, but you can see the XI strip between here and here, and you can see the indication of the subintervals that we get when we partition Y from negative square root of A squared minus X squared, XI squared to plus the same expression. And we see that the stack in the middle is the highest, and as we get out toward the edge, the stacks get lower. Okay, so when we do the sum along the XI strip, what do we have? Well, the dimensions of the strip are delta Xi by delta Yij, and our Z for each strip goes from 0 to Zijk, from Z, well, doesn't matter, we're not summing that, okay? Within the Xi strip, the Y's go from, Y's are partitioned from J equals 1 to M sub I, so we have this as the volume of the Xi strip. So we can see this whole thing as an approximation of the volume of one slice of the sphere. Okay? So we sum the volumes of all those stacks. Well, this is the sum of the volumes for all the stacks in the Xi strip. Try to follow my words here. The total volume you get by adding up all these. Okay, so you have to add all these up over your Xi's. So you're going to have to add them up for I equals 1 to n, because there are n Xi strips making up this picture. I'm not going to attempt to sketch that. We have strips running from here all the way over to the back of this thing. Okay, we add them up, and those we get the sums of the volumes. Now, I think it's important to be able to write down the partitions, but what it then comes down to is, since you can describe the sphere by this set of inequalities, well, each set of inequalities tells you what interval needs to be partitioned. Okay? So the x interval is partitioned from negative a to a. If you're doing the whole sphere, it'd be negative a to a. Now I've only done a hemisphere. If I want to do the hemisphere, I'd have a 0 here, right? If the whole sphere x would be from negative, well, actually, never mind, you wouldn't go from 0 to a. Okay, x would go from negative a to a. Y then, for given x, would go from negative square root of a squared minus x squared to the square root of a squared minus x squared. Then for given x and y, z would have to go from negative square root of a squared minus x squared minus y squared to the square root of a squared minus x squared minus y squared. Now, as if you're doing the whole sphere, if you're just doing the upper hemisphere, then z would just go from 0 up to this limit. If you're doing the lower hemisphere, you'd go from this negative limit up to 0. If you're doing between, a slice of the sphere, between two z values, well, you have z going between those two z values. Okay, well, that's kind of a picture of volume integration and mass and attendant quantities in rectangular coordinates. Now, not every surface is a sphere. No, we do it for paraboloids, we do it for quadric surfaces, we do it for all kinds of weird surfaces. It's the same, except of course these expressions for the limit wouldn't be the same. Sometimes they're even simpler than this, and sometimes they're extraordinarily complicated.